I want to real quick address a great question that came up about this chi-square test statistic. First of all, I put this up only for a conversation piece. That's the actual equation that generates the curve. Every curve we deal with in this class, whether it's a t-curve, whether it's a z-curve, whether it's a chi-square, later on in some stat classes you might deal with the ANOVA, that's an F test, an F distribution, which is really just the ratio of two chi-squares. They all have an equation that goes behind them. I take great pride in not tormenting you with the equations, because if you have the equations, the only way to deal with the equations is to do calculus. You have to then fill them with rectangles and add up rectangle areas. So that's why we use technology, which does the area for us. But the question was, what exactly is this number, this 116 in this case for the M&Ms? So this curve we looked at briefly in class on either Thursday or Tuesday, because Thursday was Thanksgiving. The idea of this curve, like the t-distribution, it changes depending on your data, depending on how you categorize your data. For example, the M&M experiment, there are 6 different categories of data: red, yellow, green, blue, and 2 others I can't remember right now. So I'm going to change that up here. Thank you, Chris. Thank you, guys. I'm going to change the number of categories to 6. That changes the degrees of freedom, which is one of those funny little terms in statistics that means less and less to us, to 5. It's always going to be 1 less than your number of categories. You don't have to worry about that. Your TI, the program I wrote for you, takes care of that. But this is what that curve looks like. This is the curve of the chi-square distribution of 6 categories. So this would look this way, whether you're talking about 6 colors of M&Ms or the 6 regions of Oregon: northeast, northwest, north central, southeast, southwest, south central. It would look exactly the same. You're testing for variance from assumed proportions. If there is absolutely no variance whatsoever from the proportion, so suppose, for example, we got exactly what we were supposed to get from the M&Ms, where would our test statistic land? Where would our test statistic land if we had absolutely no variance whatsoever?
0.
It would land right at 0 for 0 variance. As you can see by the curve, that's highly unlikely to happen. The curve isn't 0 at 0. It basically goes to the origin right there. So what the curve knows, slickly I think, is that you shouldn't have no variance. You should have some variance from the average because you're drawing a sample. You have to have sampling error. So as you move away from that, it gets more likely to have a certain amount of variance. But when it gets too far away from the 95%, that's when you start getting into the region of, okay, now there's too much variance somewhere. We were at 116. Can you see 116 on this curve? No, it's out too far. It's way the hell out there. It's basically almost double where it is right, or 1.5 times where it is right now. Make sense? So in other words, we saw too much variance. The way I set this curve up, and I wish I could have a graph, we would put in the p-value of 116. Oops. Crap, should have done that. Undo. 116. There's your p-value right there. 2.2 times 10 to the negative 23rd. Which means it is possible that Mars is correct, and we just got deviant data. It's possible, yes? Which means we made a what? I'll give you a good sized hint up here.
Type 2.
Careful. I'm giving you a good sized hint up here. False positive. We said something's wrong.
I think I saw 2.
Oh, that was my pinky. My pinky was something like this. Sorry. Damn it. Old heavy metal habits. Type 1 error, potentially. But this is why, this is the perfect example. We've often been asked questions like, well, okay, if you think it's a type 1, how can you rectify that? Or if you get a p-value, Laura, you asked this one I think back in the day, if you get a p-value close to 5%, what do? What's my stock answer to that every single time?
Get more data.
Get more data. That's why I love the fact we've run this thing like 25 times. The data that you just signed your name off on represents like 25 different tests of data that I've done over the past 8 years. The same results happen every time. What would the chance of us getting a type 1 error every single time be? What do you think? What is the chance of a type 1 error in any given test? 1 in 20. What's the chance of a type 1 error in 2 successive tests? I'm going 243 on you now because I'm faster. 1 in 20 squared. 1 in 400. What's the chance of type 1 error in 3 successive tests? 1 in 8,000. 1 in 20 cubed. What's the chance of a type 1 error in 25 successive tests? Say it. Say it. What's it effectively equal to? 0. It's effectively equal to 0. Now, there's a different question. What's the chance of a type 1 error in at least one of those 25 tests? That's guaranteed almost. That's guaranteed, especially if you've done 25 of them. But the thing is that if you're getting multiple type 1 errors, false positives, there's a problem with your test. I fail to see how this is a problem with our test. All we're doing is counting and testing them against what they're telling us they should be. There's no like glitch going on. There's no non-sampling error happening here. You see what I'm getting at, friends? So this is like, I love ending with this experiment because although it's a little bit ridiculous, testing candy colors, it ties into everything that we've talked about all class. All class. And it even goes beyond, which we'll talk more about on Thursday when we get back together again. Fair? So Will, that's what you're actually looking at. Now, as the degrees of freedom go up, this thing does walk this way and then becomes more bell-shaped. The limiting value of this goes off too. There's enough of this. That guy right there, this is getting a little bit mathy, but this guy right here is similar enough, I'm assuming, to the normal distribution that as n or k in this case goes off to infinity, the thing actually limits to a bell curve. But that's getting way too mathematical, and I will never have you doing like 120 categories on an exam with a TI. It's ridiculous. Cool? Great questions. Great questions. Make sense? Let's summarize. Let's summarize and call it a day. Call it a class for that matter. I want to summarize where we've been. Well, maybe where you're headed next. Maybe where you're headed next. Would you mind throwing the light back on, Will, if you don't mind? So what we have done, and I've given you, you'll see this in your homework. I put an Excel, I'll show it to you before you leave. I put an Excel spreadsheet in the next 2 homework assignments. We're only going to get to 1 homework. We won't get to both of them. The goodness of it is an Excel flowchart that lets you know, you can use it later on in your lives when you have to run your own hypothesis tests, where it says, okay, what do you want to test? You come in like with an arrow, and then it says you're testing a single proportion, a single mean, double proportion, double mean, triple proportion, triple mean, and it kind of like shows you what you should go and what decisions you should make based on it. But basically, roughly, what you have here in the world of hypothesis testing, we broke this part of the course into 3 sections, really. And we just kind of wrapped up the last bit. The first section was a single parameter. Of those, my favorite is the matched pair t-test. That was my favorite from back in the day, because it's the most useful. It's the one you guys probably will actually see in research. The other 2 are nice pedagogically, the one prop z's, and the t-test itself, just the simple t-test. And they're nice. They're nice, they're good. They're a little bit fictitious though. And the fiction occurs in that you have to know a value that you're testing against. So you can do that. For example, the CDC and the flu vaccines. You know that it was 70%. If you can exceed 70% of the antibodies, the vaccine's working. With IQ, you know if you're changed from 100, something's changed. So you know these things. You know these things. And they're great, but the matched pair was my favorite of this whole bunch just because you don't have some fictitious superfluous value. You just start at 0. 0 means nothing changed. Greater than 0 or less than 0 means something did change. That's good. That makes me happy. So that was single parameter. Double parameter, 2 parameter. This is where we got into next. And we spent quite a bit of time on this. The double parameter tests were when you had 2 independent either proportions or means. Oops. Oh, which reminds me, I still have to return to you guys. And these looked extraordinarily similar to these as far as name goes. This was called a 2 prop z. And this was called a 2 sample t. And they're beautiful. And they're beautiful. And there's built-ins for them. Very often you'll hear about t-tests when you look at statistical results, whether in the literature or in your next stat classes you take, if you take any more. So t-tests are wonderful. The problem with all these tests, every single one of them has the assumption built into it that it has to be bell-shaped, it has to be binomial, it has to be normal, it has to be symmetric unimodal with no outliers. There's all kinds of restrictions that are on that. There are alternatives to all of these. One of the things I want to have you do on your out-of-class exam is to go find the non-parametric alternatives to these things. You have to do some Google searching. So basically you have to go into Google and say, what's a non-parametric alternative to a t-test? And it'll give you a whole bunch. You'll have to write one in the exam and send it back to me. Because this is the kind of thing, you might need that at some point, at least to understand. If you're reading along a journal and the test statistic comes up U, the letter U, and you're going through 244, you're like, well, Sean talked about Z, and then he talked about T, and then he just talked about chi-square. He never mentioned U. Well, that's because U is a non-parametric test statistic. When you look at your out-of-class exam, I did the C test recently. I thought it was the J test. My wife's going to kill me if she finds out. I thought I called it the J test because my wife's name is Jen. But as it turns out, I was listening to The Clash. So I called it the C test when I made the test up. But this is the thing, we just make up these letters. These letters don't mean anything. They're just, it's a way to label a test statistic. And then put a p-value with it. So if you're reading along in the journal, and you're like, okay, the test statistic is now smiley face star, and its value is 21, you're like, what the hell is that? And you read down p-value is less than 5%, and you go, oh, I got it. I don't even need to know what the distribution is that they're using. The p-value is less than 5%, so what happened? Something, Danielle, thank you, say nice aloud. Something changed. That's the kicker. If the p-value is less than 5%, I don't care what test you're running, something changed. Now, in your out of class, you'll formalize that a little bit more. You're going to fix Pam Purdue. That was her tag name on the thread that I found out. She had the wrong answer. You're going to fix Pam Purdue's answer. Anyway, when we get into multi-parameters, more than 2 parameters. More than 2 parameters. More than 2 just means 3 or more, essentially. So there's 2 classifications for that. There's multiple proportions, and there's multiple means. Multiple proportions and multiple means. This is the one we talked about in class. This is the goodness of fit. That's the goodness of fit. The Goff test, the goodness of fit test. And it's wonderful. And it makes us happy. For a whole bunch of reasons. This is one I'm not going to rush to get into it. I don't want to. It's called the ANOVA, the analysis of variance. I make reference to it on your out-of-class exam only because I want you to do a little Googling and find out what a non-parametric alternative to it is. That's what I want you to find out. What's a non-parametric alternative to it? So in other words, that particular test, the ANOVA test, is just like a 2-sample t-test, except it's like a 3 or 4 or 5 or 6 sample t-test. And because it's basically the same idea as those t-tests, you have to have bell-shaped data, and you have to have certain restrictions on variances, all these restrictions you have to have. Your job is going to be to go find some other test that does the same thing, tests a bunch of means, but doesn't require all those assumptions on the data itself. But you'll see all that when you look at the out-of-class exam. What is your exam Thursday? I think it is, yeah?
Yeah.
You're in class next week, so a week from Thursday. That's when your out-of-classes do as well. So, okie doke. And that, I think, is a decent place to call a class. So on Thursday, we can chit-chat about Goff homework. Make sure you guys understand that. Also bring any other questions on previous homework. The last exam in class is not cumulative. It'll just go back to what the previous exam stopped at, which I think stopped here. I think it stopped here. So we'll just have this third exam be on these guys. So bring some questions on Thursday. Okay, doke? All right, bring your projects too. Oh no, don't bring them. Email them to me before Thursday. Yeah. Email them before class on Thursday. That's the deal with those. There's one last quiz. And if you want to stick around, I've got stuff to return. Otherwise, I just give it to you on Thursday. All right. Trying to catch the target. I am. Dina, here you go. Justine says she wasn't going to be here. Kelsey. Go. Eric's up there.
The last expansion meeting is in Cascades, 118 free pizza at lunchtime.
What's the expansion meeting?
For the OSU expansion.
Oh, we're talking about that.
Yep.
Huh, Harrison, I never got graded. So I'm going to send it back in. What's your project? You never got graded, so I'm going to send it back in and get it graded. What's going on? Chris, I found out what happened with this. Yes, you goofed up here, these numbers are too big, but everything you did past that was fine. So I just stopped the point on the calculation. I don't know what happened, but everything else was fine, things went well. So, not to worry about that.
This
Yeah.
I read over it last night.
Oh, so that was my 4 points for my.
Yes, so we'll get that points back, we'll get the points back to you.
Okay.
Just bring it in, we'll get the points back.
Okay.
Not a problem.
yeah. I served him a couple drinks, dude.
Yes.
No alcohol, man.
Harrison, we got an out of class for you. I think I can turn that off now, yeah?